Preparing for a Siemens Embedded Systems Engineer Drones interview? You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design sensor fusion for a drone using IMU, GPS, barometer, and magnetometer data? Sensor fusion is about estimating attitude and position from noisy, imperfect sensors. In a drone, I would run the IMU at high rate for short-term motion, then correct drift using GPS, barometer, optical flow, or magnetometer. An EKF is common because it models nonlinear motion and sensor covariance. I would also handle calibration, timestamp alignment, vibration filtering, and outlier rejection. Bad fusion usually shows up as drift, jumps, or unstable control. While answering, focus on complementary filtering, EKF concepts, sensor update rates, covariance, calibration, timestamp synchronization, vibration effects, drift correction, and how fuse state estimates feed the flight controller. Question 2. What real-time constraints matter most in a drone flight controller? The key constraint is predictable timing, not just fast execution. A flight controller must read sensors, estimate state, run control loops, and update motors within fixed deadlines, often hundreds or thousands of times per second. Jitter can destabilize the aircraft even if average CPU usage looks fine. I would prioritize control and IMU tasks above telemetry or logging, measure worst-case execution time, use watchdogs, and keep interrupt handlers short. Determinism beats clever complexity here. Make sure to cover deterministic loop timing, control frequency, interrupt latency, scheduling jitter, watchdogs, priority inversion, sensor deadlines, actuator update deadlines, and the difference between hard and soft real-time tasks. Question 3. Explain how a PID controller is used to stabilize a quadcopter. A PID controller converts attitude or rate error into motor commands. In a quadcopter, I usually think in cascaded loops. An outer attitude loop produces desired angular rates, and an inner rate loop drives the motors. P reacts to current error, I removes steady-state bias, and D damps fast changes. I would tune rate loops first, add anti-windup for saturation, filter derivative noise, and validate with logs. Poor tuning causes oscillation, sluggish response, or drift. In your answer, talk about proportional, integral, and derivative terms, cascaded attitude and rate loops, tuning strategy, saturation, anti-windup, noise sensitivity, and motor mixing for quadcopter control. Question 4. How do PWM, DShot, and CAN-based ESC control differ for drone motors? PWM is simple. Pulse width maps to throttle, but it is slower, less precise, and more exposed to timing noise. DShot sends digital throttle values with checksums, so calibration is easier and command integrity improves. Some ESCs also support bidirectional telemetry for RPM feedback. CAN-based ESCs are better for larger drones because they support robust networking, diagnostics, and longer wiring. The trade-off is firmware and bus complexity, so the protocol choice depends on vehicle class and reliability needs. Be sure to mention signal timing, latency, noise immunity, bidirectional telemetry, implementation complexity, synchronization, failure detection, and why modern drones often prefer digital ESC protocols over analog PWM. Question 5. What would you check if a drone has random attitude spikes during flight? I would start with flight logs, not guesses. Attitude spikes can come from IMU vibration, timestamp glitches, magnetometer interference, power rail noise, or estimator outlier handling. I would compare raw sensor data, EKF innovations, CPU load, and control outputs around the spike. On the bench, I would test motor-induced vibration and EMI, because issues often appear only under throttle. If raw sensors are clean, I would inspect synchronization, buffer handling, and race conditions in the estimator path. While answering, cover systematic debugging, logs, sensor timestamps, IMU vibration, power noise, EMI, bad calibration, EKF innovation checks, firmware race conditions, and reproducing the issue on bench or simulator. Question 6. How would you implement failsafe behavior for loss of radio control or GPS on a drone? Failsafe design starts by defining safe states for each failure. If RC is lost but GPS and battery are healthy, return to home may be appropriate. If GPS is lost, the drone may switch to altitude hold, land, or use optical flow if available. I would detect failures with timeouts and health checks, avoid abrupt mode changes, and log the reason. Failsafe must be tested heavily because a wrong recovery action can be more dangerous than the original fault. Make sure to cover failsafe states, signal timeout detection, return to home, land now behavior, geofencing, battery state, sensor health, redundancy, user configuration, and safety certification considerations. Question 7. What are common sources of noise in drone embedded systems, and how do you mitigate them? Drone electronics are noisy because high current motors and fast-switching ESCs sit near sensitive sensors. I would mitigate electrical noise with good grounding, short return paths, decoupling capacitors, shielding where needed, and separation between power and sensor traces. For vibration, I would use mechanical isolation and proper IMU placement. Software filters help, but they add phase delay, which affects control stability. The best solution combines PCB layout, power design, mechanical damping, and careful signal processing. In your answer, include electrical noise, motor EMI, switching regulators, ground loops, vibration, ADC filtering, shielding, PCB layout, decoupling capacitors, sensor placement, and software filtering trade-offs. Question 8. How do you manage communication between a flight controller, companion computer, GPS, telemetry radio, and sensors? I separate communication by criticality and bandwidth. High-rate sensors like IMUs usually use SPI with DMA for low latency. GPS and telemetry often use UART, while CAN is useful for distributed nodes and ESCs. Navlink is common between flight controller, ground station, and companion computer. I would use CRCs, timeouts, sequence numbers, and clear packet framing. Control critical data should never be blocked by logging or video-related traffic, so prioritization and buffering matter a lot. Be sure to discuss UART, SPI, I2C, CAN, Navlink, bandwidth, latency, bus arbitration, DMA, error handling, packet framing, CRCs, and separating critical flight traffic from non-critical telemetry. Question 9. How would you choose between bare metal firmware and an RTOS for a drone controller? Bare metal works well when the system is small, timing is simple, and a superloop plus interrupts is easy to reason about. An RTOS helps when the drone has multiple concurrent functions: estimation, control, logging, telemetry, mission handling, and health monitoring. I would choose an RTOS if priorities, timers, queues, and modularity reduce risk more than they add overhead. The danger is hiding timing problems behind threads, so I would still measure latency, stack usage, and worst-case execution time. While answering, compare determinism, scheduling complexity, memory footprint, driver reuse, task isolation, debugging, certification, priority scheduling, interrupt design, and when simple superloops are better than RTOS tasks. Question 10. What bootloader and firmware update strategy would you design for field-deployed drones? For field drones, firmware updates must be safe against power loss and bad images. I would use a small protected bootloader that verifies signatures and CRCs before booting an application. Dual bank or AB firmware allows rollback if the new image fails health checks. Updates should include version metadata and hardware compatibility checks. Over telemetry or USB, I would throttle and validate chumps. The goal is simple: never let a failed update brick the flight controller. Make sure to cover secure boot, image validation, rollback, dual bank flash, power loss safety, versioning, signing, CRC checks, telemetry-based updates, and how to avoid bricking aircraft in the field. Question 11. How do you estimate and optimize power consumption in a drone embedded system? Power optimization starts with a budget. Motors dominate, but avionics still affect endurance and reliability. I would measure current draw per subsystem, account for voltage sag under load, and choose efficient regulators with enough thermal margin. Sensors and radios can be duty cycled when mission phases allow it. The firmware should monitor battery voltage, current, and remaining capacity to trigger safe behavior. Saving a few watts matters, but not if it compromises sensing, communication, or flight safety. In your answer, talk about battery chemistry, current sensing, voltage sag, power budgets, regulator efficiency, sleep modes, sensor duty cycling, telemetry power, thermal limits, and flight time trade-offs. Question 12. How would you debug a hard fault or memory corruption issue in flight controller firmware? I would first capture the fault context, program counter, link register, stack pointer, fault status registers, and task state if an RTOS is used. Then I would map the address back to code using the elf and map file. Common causes are stack overflow, invalid pointers, DMA buffer misuse, race conditions, or writing past array bounds. I prefer static allocation in flight firmware to reduce heap surprises. Reproducing under full sensor, logging, and telemetry load is critical. Be sure to include fault registers, stack traces, map files, stack overflow checks, heap avoidance, bounds checking, race conditions, DMA buffers, logging strategy, and reproducing issues under realistic load. Question 13. What calibration steps are important before a drone is safe to fly? Calibration turns raw hardware into trustworthy measurements. Before flight, I would calibrate gyro bias, accelerometer scale and orientation, magnetometer hard iron and soft iron effects, radio endpoints, and possibly ESC throttle range. I would also check sensor mounting orientation and level horizon alignment. For higher quality systems, temperature calibration matters because IMU bias changes with heat. Calibration should end with automated pre-flight checks, not blind trust. A drone that takes off with bad calibration is already in a failure mode. While answering, cover IMU bias calibration, accelerometer scale, magnetometer hard/soft iron compensation, ESC calibration, radio endpoints, level horizon, compass interference, temperature effects, and validating calibration with pre-flight checks. Question 14. How would you design geofencing and no-fly zone enforcement in drone firmware? Geofencing is a safety constraint layered on top of navigation. I would represent zones as polygons with altitude limits, then evaluate the drone's estimated position with GPS accuracy margins. The firmware should warn before reaching a boundary and command a controlled stop, loiter, return, or land, depending on context. Hysteresis prevents mode flapping near edges. I would also handle stale maps, GPS loss, and spoofing indicators. Enforcement must be predictable. Sudden aggressive corrections can create new hazards. Make sure to discuss GPS accuracy, polygon boundaries, altitude limits, hysteresis, failsafe response, map updates, spoofing concerns, operator feedback, regulatory constraints, and avoiding sudden unsafe maneuvers at fence boundaries. Question 15. How do you validate drone embedded software before real flight testing? I validate in layers before risking hardware. Unit tests cover math, filters, parsers, and safety logic. Software-in-the-loop tests mission and control behavior in simulation, while hardware-in-the-loop checks real timing, drivers, and interfaces. On the bench, I run motors without props, replay sensor logs, and inject failures like GPS loss or low battery. First flights should use conservative limits and clear abort procedures. Good validation is incremental. Every stage should reduce unknowns before the next one. In your answer, include unit tests, hardware-in-the-loop, software-in-the-loop, simulation, bench tests with props removed, log review, fault injection, sensor replay, safety checklists, and incremental flight envelopes. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.